A dimension is simply a direction you can move in, independent of every other direction. Left and right is one dimension. Up and down adds a second. Forward and backward adds a third. That is the world you live in. 3 directions, 3 dimensions of space. Add time as a 4th axis, and you have what physicists call space-time, the standard model of reality. But here's where it gets strange. The number of dimensions is not just a counting exercise. It determines the fundamental rules of the universe. Change the number of dimensions, and you change how gravity works, how particles behave, and even whether stable atoms can exist. A universe with 4 spatial dimensions, for instance, cannot sustain stable planetary orbits. The gravitational force would fall off too quickly with distance, and planets would spiral inward or fly outward rather than follow steady paths. This suggests the 3 dimensions we inhabit are not arbitrary. They appear necessary for structure and stability. Whether that is coincidence or something deeper, physicists cannot yet say. A zero-dimensional object is a single point. It has no length, no width, no depth. It occupies no space at all. In classical mathematics, you can pack infinitely many such points into any region, no matter how small. Physics, however, imposes a hard limit. Quantum gravity research strongly suggests that space itself is not infinitely divisible. Below a scale of approximately 10 to the power of negative 35 meters, known as the Planck length, the concept of a distinct point stops making sense. Space becomes granular. The smooth continuum of geometry breaks down into something more like a foam or a mesh. What is deeply strange is what this implies about dimensionality at these scales. Several independent quantum gravity calculations, including those from causal dynamical triangulations and loop quantum gravity, find that at Planck scale distances, space-time behaves as though it only has about 2 effective dimensions, not 4. The volume of a tiny region stops scaling the way it should in 3 dimensions, and instead scales like an area. This phenomenon is called dynamical dimensional reduction, and it means the familiar dimensionality of space may be a large-scale feature that emerges from something fundamentally lower dimensional beneath it. In other words, when you zoom into reality far enough, the 3rd dimension you take for granted appears to vanish. The universe at its smallest may be nearly flat. If that's true, then the depth you experience every moment may only exist at large scales. One-dimensional space is a line. Any object in this space can only move forward or backward along a single axis. There is no sideways, no up or down. You would be trapped on a track with no escape. This may sound trivial, but one-dimensional objects are at the foundation of the most ambitious theory in modern physics. String theory proposes that the fundamental building blocks of nature are not point particles, but tiny, one-dimensional strings vibrating in higher dimensional space. The strings have no width and no interior. They are pure one-dimensional loops or strands. What makes this powerful is that different vibrational modes of the same string correspond to different particles. A string vibrating one way looks like a photon. Vibrating another way, it behaves like an electron. A third mode produces what appears to be a graviton, the hypothetical carrier of gravity. This single framework attempts to unify all forces and all particles under one set of equations. The reason physicists moved to strings in the first place is that point particles cause infinity problems in quantum calculations, particularly when gravity is involved. A point has 0 size, which generates mathematical singularities when you try to calculate interactions. Replacing points with extended one-dimensional objects smooths out these infinities. Gravity, which resists quantization at 0 dimensions, becomes manageable at 1. The price is that the mathematics only works consistently if the strings vibrate in more than 4 dimensions, which immediately pushes the conversation upward into higher dimensional space. 2 dimensions is a flat surface. 3 dimensions is the space you move through every day. These feel like settled territory, but modern physics has revealed something unsettling about both. General relativity describes 3-dimensional space not as a rigid background, but as a flexible fabric. Massive objects curve this fabric, and that curvature is what we experience as gravity. A star bends space around it. Earth curves slightly around the sun. You are not being pulled toward the ground. You are following the curved geometry of space-time near a massive planet. On the very largest scales, cosmological measurements show that the overall curvature of 3-dimensional space is extraordinarily close to 0. The universe is, to a remarkable precision, flat. Not flat as in 2-dimensional, but flat as in not curved in any direction. This near-perfect flatness is itself a mystery requiring explanation, and inflation theory was partly developed to account for it. But zoom back down toward the Planck scale and the geometry changes again. Calculations using quantum group symmetries suggest that spacetime has a fractal character at very small distances. The effective dimension of space changes depending on the scale at which you measure it. At large scales, you get the familiar 4 dimensions of spacetime. As you zoom in toward the Planck scale, the effective dimension flows downward toward 2. The smooth space you inhabit may be a large-scale average of something far more primitive beneath. The 4th dimension is time, and Einstein showed it is not separate from space. Together, 3 dimensions of space and 1 of time form a single 4-dimensional structure called spacetime. Time is not a clock ticking in the background. It is a geometric axis of the universe that bends, stretches, and warps like space. One of the most philosophically disturbing ideas this produces is the block universe, or eternalism. In a block universe, every moment in time exists simultaneously as a static 4-dimensional structure. Past, present, and future are all equally real, like a loaf of bread. The sense that time flows, that the present is special, that the past is gone and the future not arrived, is an artifact of consciousness moving through the block from one slice to the next. If that idea unsettles you, it should. A competing idea, the growing block universe, states the block is not complete. It extends from the fixed past to a leading edge of the present, with new slices constantly added. The future does not yet exist. On this view, time genuinely moves forward, and the universe is actively being created. Both views hinge on entropy. The universe began in a low entropy state and has grown more disordered since. Yet the equations of physics are nearly time-symmetric. Why the beginning was so ordered remains unresolved. The 5th dimension is where things get speculative, but not without strong physical motivation. In 1921, mathematician Theodore Kaluza showed that if you add a 5th spatial dimension to Einstein's equations and curl it into a tiny circle, the equations naturally split into 2 parts, one describing gravity and one describing electromagnetism. A single geometric framework produced 2 forces. Oscar Klein later proposed that this 5th dimension was too small to detect, compactified into a loop perhaps at the Planck scale. The Kaluza-Klein idea was largely forgotten for decades, then revived by string theory, which requires not 1 but 6 extra spatial dimensions, beyond the 3 we observe. In string theory, these dimensions are not simply curled into circles. They are wrapped into extraordinarily complex geometric shapes called Calabi-Yau manifolds. These are 6-dimensional surfaces of incredible intricacy, with tunnels, holes, and topological features that determine the physical properties of our universe. Here is what makes this genuinely strange. The shape of these hidden dimensions controls everything. Different Calabi-Yau geometries produce different numbers of particle families, different coupling constants, and different values of fundamental forces. Our universe, with its specific 3 families of quarks and leptons and its particular set of constants, could correspond to one specific Calabi-Yau shape out of an almost incomprehensibly large collection. String theorists estimate the number of possible shapes at 10 to the power of 500 or more. This collection of possible universes is called the string theory landscape, and it raises the possibility that our particular physical laws are not uniquely determined, but are instead the local conditions of one region in a vast multiverse. Superstring theory requires exactly 10 spacetime dimensions to be mathematically consistent, meaning 9 dimensions of space and 1 of time. Remove even 1, and the equations generate impossible results, like negative probabilities and infinities that cannot be removed. 10 is not a choice, but a mathematical necessity of the framework. The 6 extra spatial dimensions beyond our 3 are hidden by compactification, meaning they are curled up at scales so small they cannot be probed by any current experiment. Dedicated experiments have tested Newton's law of gravity down to about 0.2 millimeters and found no deviation, placing tight limits on how large any extra dimensions could be while remaining undetected. But one class of theoretical models, called large extra dimension scenarios, proposes that some extra dimensions could be as large as a fraction of a millimeter. In these models, ordinary matter is stuck on a 3-dimensional membrane within a higher dimensional space, while gravity is free to spread through all dimensions. This would dilute gravity across extra dimensions and explain why gravity is so much weaker than the other forces of nature, what physicists call the hierarchy problem. Higher dimensional black holes in these models behave in ways that are impossible in 4 dimensions. In 4 dimensions, the only stable black hole configuration is roughly spherical. In higher dimensions, black holes can form rings, tubes, and other extended geometries. A black ring, for instance, is a black hole shaped like a donut with a genuine hole through the center, something that cannot exist in our observable 4-dimensional world. These exotic configurations have been analyzed mathematically and represent one of the clearest signatures of extra dimensions that could in principle be detected. In the mid-1990s, physicist Edward Witten showed that the 5 different versions of string theory that had been developed were not actually competing theories. They were all different limits of a single, deeper framework living in 11 dimensions, called M-theory. The 11th dimension is not just another curled-up direction, it fundamentally changes the nature of the objects in the theory. In 10-dimensional string theory, the basic objects are one-dimensional strings. When you add the 11th dimension, strings can expand into two-dimensional membranes, called two-branes, or into higher dimensional surfaces called p-branes, where the number p indicates how many spatial dimensions the surface has. Our entire observable universe may be a three-brane, a three-dimensional membrane floating within the 11-dimensional bulk of M-theory. The implications of this picture are difficult to fully absorb. Gravity, unlike the other forces, is not confined to our three-brane. It leaks into the bulk. This is one proposed explanation for why gravity is so extraordinarily weak compared to electromagnetism and the nuclear forces. The gravitational force is being diluted across 11 dimensions, while the other forces are concentrated entirely on our brain. M-theory also provides a potential mechanism for the Big Bang. In some models, our universe was created when two parallel branes collided, and the energy of that collision was deposited as the hot, dense plasma of the early universe. The Bang was not the origin of everything. It was a collision between two surfaces in a higher dimensional space. Everything discussed so far involves extra dimensions of space. But there is a far more disturbing class of theoretical work: extra dimensions of time. Our universe has one time dimension, a single axis along which events are ordered from past to future. Add a second time dimension and causality, the rule that causes must precede effects becomes extraordinarily difficult to preserve. Two independent time axes mean that from one perspective, event A causes event B, but from another equally valid perspective in the second time direction, the ordering is reversed. Most attempts to build consistent physics with two-time dimensions fail precisely for this reason. Recent work has nonetheless explored whether three-time dimensions could form the primary structure of reality, with three dimensions of space being derived or secondary. In this proposal, what we call space is not a fundamental arena, but an emergent property arising from deeper temporal structure. The argument is highly speculative and far outside mainstream consensus, but it has been published in peer-reviewed contexts and represents an active line of theoretical inquiry. What makes multi-time theories viscerally strange is that conventional notions of before and after, and therefore of cause and consequence, become direction-dependent in a temporal space with multiple axes. The feeling that time has a single, fixed direction, that you are moving through it rather than through space, may be a highly parochial feature of living in a universe where only one of many possible time axes is accessible. Whether that is the case, and whether it could ever be tested, remains entirely open. The strangest possibility of all is that dimensions are not fundamental at all. Some of the most significant theoretical work of the last 3 decades suggests that both space and time may be emergent properties arising from something more fundamental, something that has no spatial or temporal character on its own. The clearest evidence for this idea comes from the ADS/CFT correspondence, proposed by Juan Maldacena in 1997. This framework shows that a theory of gravity in a higher dimensional space is exactly equivalent, in a precise mathematical sense, to a theory with no gravity at all on a lower dimensional boundary. A full, three-dimensional gravitational interior can be completely described by a two-dimensional surface the way a hologram encodes a three-dimensional image on a flat surface. This is the holographic principle, and it implies that one of the dimensions of the interior is not independently real. It is encoded in the boundary. More recent work extends this idea to the emergence of time itself. In certain quantum gravity models, time appears as a consequence of entanglement between quantum systems, not as a pre-existing background. Two systems that are quantum mechanically entangled can generate the appearance of time passing, even in a universe where the fundamental equations contain no time variable at all. If this is correct, then the dimensions of the universe, including the three of space and one of time that you experience every moment, are not built into reality at its deepest level. They are macroscopic features of a universe that is, at its foundation, something far stranger and more abstract. What that foundation actually is, and whether it can ever be directly observed or described, remains the central unsolved problem of theoretical physics. Which possibility unsettles you most? Hidden spatial dimensions, extra time axes, or the idea that dimensions aren't fundamental at all? Let me know in the comments below. And if you want to keep exploring the deeper layers of reality, subscribe and check out this video next. Thanks for watching.